Hello, my name is Ugo. So this is valid Sudoku. I should probably just open it up over here. Valid Sudoku. So, this is the problem. We are given a 9 by 9 grid. It is, in Python, it is a 2D list. String elements within the list, the second list or whatever. So we have a list of rows, and then each column is populated by a string that's either a number, 1 through 9, or the character dot or period to represent the lack of a number there. So yeah, and then we're basically just trying to determine whether or not the Sudoku is valid, and a valid Sudoku just means that each row, column, and 3 by 3 grid, which represents the little boxes of 3 by 3 starting at 0, 0, are or do not contain duplicates. So every row, every column, and every 3 by 3 block or box or grid or subgrid, I call them softbox. I call them subgrid, but yeah, subbox. Basically, we just have to make sure that there is no duplicates within a subbox, the row, or the column. A valid Sudoku does not have to have an answer. So it says right here, a note. And I mean, I remember this because I've played the game a little bit sometimes, and sometimes there is just not a solvable or a solution to it. So yeah, a Sudoku board to be valid does not have to be solved. So we only have to make sure that there's no repeats in the same row, column, or 3 by 3 grid. We don't have to worry about whether or not it's solvable, which is very helpful because then that would add like another layer of complexity to this. So that's the type of input we get, and we just want to return a Boolean true or false, whether or not it is a valid Sudoku board or table from the start. The constraints, I believe LeetCode has them. I don't think they're on here. The constraints are the length of the board and the length of the board's columns. No, the number of rows and the length of each row is 9. So it's going to be a 9 by 9 grid all the time. And the only things that we can have here is a digit of 1 to 9 or a period. Both of them are going to be represented as strings, as you can see here in the input. Yeah, with that knowledge, I thought back, okay, since we're only really checking if there's duplicates within this list, or this row, this column, and this like 3 by 3 matrix, I thought back to the has duplicate or contains duplicate problem that I did a couple of weeks back. And in that one, I think the most effective solution was just to make a list, or to make a set out of the list that you currently have. And if the length of the list is smaller than or if the length of the list doesn't match the length of the set that you created from that list, that means that there is a duplicate somewhere in the list, or at least a minimum of one. Yeah, that's kind of what I used to, I based everything off of that. And I saw that basically we could just create lists based on what we're checking for. So for the rows, that was simple. You just have to access the index of that row in the grid, and we could just pass that in really quickly into the has duplicates. Then right here in the columns, we just had to do a little trick. It's not anything crazy. We would just have to go through every row and then just only get the values at the current index that we're checking, so the current column that we want to check. In the rows, for every row in the board, we're just checking that index's that index, the value at that index. So we're just going, okay, row 0, index 0, okay, next row, row 1, index 0, and we just keep going down. So that gets us the column. And we could do a for loop with that, so then we can go through each column individually. The columns was pretty simple. It was just a little, took me a little bit to like visualize how I would do it in Python. And then the final one was the trickiest of them all, but I also remembered, I love 2D, I love matrices. I love grids like this in programming, because a lot of the time you can just use the technique to flatten it and process it like a normal flat list. And usually that'll actually be very helpful. And as seen here, the solution actually needs that to be effective, I think. Well, I'm not sure if this is the most efficient. I'm pretty sure it's close. It's just, I don't know. I mean, there's not really an efficient way to check if every row, column, and 3x3 grid do not contain duplicates. It's like you have to check everything multiple times. So, yeah, and in the valid grids, all we did was we used a number I in range of the length of the board, or just 9. I could have just written 9, but I kind of wanted to relate it to the board. I didn't know which one would be more readable. So essentially, what I here is supposed to represent is the index of the grid, of the subgrid we're on. So rather than one box or one little box or element within a row or a column, we're representing I. I represents the boxes. So we have box 1, or box 0, box 1, box 2, box 3, box 4, box 5, box 6, box 7, box 8. And that makes it a lot simpler to work with and make it flat, because basically what we have to do is we have to flatten a subgrid within a larger grid. And that was a little tricky for me. So what I did was I just split it up. So then we have like a number I that's tracking the box we're currently on, or the grid that we're currently on. And then with that, I also made a list of starting positions that we can possibly have, because the only 3 starting positions that we can possibly have for a 3x3 grid within a 9x9 grid is 0, 3, or 6. And that repeats in the columns too. So that becomes very useful to just have one little list of 3 elements. It's basically negligible amounts. I could make it into 3 integers. It's not like it's going to be O of n. I mean, we're given a 9x9 grid, creating a 3 element list with constant numbers was not going to do anything. I probably could have called it const. Wait, does Python have const? I forgot. But yeah, or I could have just, it's fine, whatever. And with that, I can flatten the subgrids first. So we're gonna have, we're gonna use I, so the number that we're currently on, 0, 1, 2, 3, 4, 5, 6, 7, 8, and we're gonna do an integer division of 3. And that gets us the row that we're currently on. So if we're at 0, 1, or 2, dividing it by 3, we'll basically round down to 0. So we'll know that we're on the first row. And then if we have like 3, 4, 5, it gives us 1, 6, 7, and 8. We'll have 2. So we get the indices of these 3 covered. And then we have column. And column is represented by modulo 3. So regardless of whether we're at 0, 3, or 6, if all of those 3, when divided by 3, will not have a remainder. So they'll all be at 0, which makes it very helpful, so we can divide the rows and the columns with the same number and handle that properly. So we can get the starting positions. So this is basically getting the coordinate position within this grid for this. I don't think it's flattening it. I'm pretty sure this isn't flattening. I don't think this would be considered flattening. I think the flattening part is this, but this would be just getting the coordinate position that we're currently on, so which grid we're on. And then in here, this is where I made a little efficiency boost. So originally I had them all separated and I kind of just did a big like double for loop. And as you can see, over 1,000 steps. I don't know why, because when I did it last time, it was only like 800 something. Well, 800 is still a lot, but for valid Sudoku, it's actually okay. It's not the best, but it's not the worst. So yeah, I changed it into a list comprehension because I realized I could just do that instead. And yeah, so we have the current row that we're at. So the row gives us the starting position of the row. So it gives us either 0, so that gives us 0, 3, or 6. But it would actually give us the rows. So it'd give us row 6, row 3, or row 0. It gives us the entire row. So now we had to j divided by 3. Oh, right. And then we had to get every row within that grid, but let's worry about that in a second. The column from earlier that we calculated will also do the same thing for its own thing. So it'll determine if we're on the first column of grids, the second column of grids, or the third column of grids. And then from there, since we had to iterate through every row and column within this subgrid, we just do the plus j divided by 3 plus j modulo 3, which basically will loop through the range of the board, which is just 9. So the nice thing that's consistent about this is that regardless of whether you're going row, column, or 3x3 grid, all of them are 9. The length of the list flattened would still be 9 regardless. So we could just use that. I think that I don't know which would be more readable, just having a 9 or board here. And then yeah, so we would do that 9 times to get the 9 elements within the subgrid, whichever one we choose. And it will be like, okay, we're starting here. The row and the column basically just choose the starting positions. So it's like the y-axis and the x-axis, and it chooses the three possible ones here. And then from there, we're just iterating through the 9 elements within that subgrid, considering the starting position. So yeah, so it'll be like, let's say we had, I don't know, what is this? 0, 1, 2, 3, 4. So let's say we had 4, or we were on subgrid 4. That would be row 4. No, row 4. So I would be at 4. And when it's I is at 4, it would be row 4 or row 1, column 1. So we would be here. It would give us a starting position of 1, 1 at this position. So it would give us 3, 3. So if we look at that, it's 1, 0, 1, 2, 3, 0, 1, 2, 3. And then that point right here is our starting position. And then from there, we're just going to be iterating forward for 9 times using integer division and modulo to go through it one by one to basically use it as a list comprehension for the grid, which will be a flattened list, a one-dimensional list. And then we just pass that into the has duplicates function up here. I think I could possibly make this more efficient in some ways, but then that would, I don't know, I think it would lessen the readability a bit, because essentially what I would have to do is I would have to put this logic repeatedly, but slightly different for each one. So for this one, since we have the row already provided by the board, I would have to keep this logic the same right here, but then I'd have to change it. So then I would add an if statement here, where it would be if row at I is not equal to dot, and then I would just repeat this condition down here. And what this does is within the generating while generating it, we could just remove or clear the periods, because those become an issue when you're trying to do the set comparison thing, where you're comparing the length with the set. So yeah, I could do that, and then but then I would have to repeat this code basically over here, and then that just removes that function entirely from being useful. So I thought maybe it would be more readable doing it this way, but you can always just add the code. It'd be like 3 lines more for in total, but then you'd also remove these 3 lines. So it's not really anything different. I just think it's less readable, and I think separating the logic a little bit would probably be more readable, as you can just be like, okay, if it has duplicates, if the current thing that we're checking has duplicates, then return false. So if the row has duplicates, return false. If the column has duplicates, return false. And finally, if the grid has duplicates, we return false. So that was my logic going in. And then finally, the is valid Sudoku that gets actually checked will just be a one-liner, nice and simple, where we return whether or not we have valid rows, valid columns, and valid grids. If one of these is not true, the and will cause it to trigger as false. And yeah, that was my solution. I believe, although it does multiple passes through everything, technically, I think the time and space complexity are O of 1, because the size is fixed, and the number of operations we are doing onto it will be fixed. So we're always guaranteed to get the number of steps we have to take. So it's like a constant, it's not growing. And same thing, or kind of similar to that, the space complexity. I never use the entire, I never make more grids or make duplicates of the total grid. I just use smaller lists, so that would be like O of n, so the biggest thing would be this thing, and relative to that, there's nothing bigger than that, or equivalent to that, because the biggest things I do is just make lists of length 9. All of them are lists of length 9, including the grid. The grid is just a flattened 3x3 made into a list of 9. So I think it's both space and time complexity of O of 1, even though it's technically a bit slow, but that's just the nature of this problem, I think. This would be 1000 steps, so this was I had all the logic inside of valid Sudoku, which just has duplicate function at the top. And then this is the separated version. It's a lot more efficient. It's less than 1000 steps. And I think the list comprehension helped a lot, because that's like the only big difference I made other than separating logic into different functions. So yeah, that's valid Sudoku. I think there's better ways to do this, probably some sort of like storing and memoization or whatever, because we're going over the same elements, but I can't think of it, because the thing is, it's still gonna be O of 1 accessing to get the numbers anyways, so it's not like a map would really help in that case. So I don't know, but yeah, that's it.